the function given is e to the x over 1 minus e to the x. For part A, we have to find the horizontal and vertical asymptotes of this function. I'm going to start off by finding the vertical asymptotes. So what you have to do, you would have to look at the denominator and equate that to 0. So you get 1 minus e to the x equals to 0. Minus e to the x, bring the 1 over, you will get negative 1. E to the x is equal to 1. Solve for x, you would get 0. Now, to find the horizontal asymptotes, I'm going to take the equation and I have to multiply this by a factor of 1 times negative e to the x over negative e to the x. Using exponent laws, I will simplify this, and what you get is negative e to the 2x over negative e to the x plus e to the 2x. Now I'm going to take the limit as x approaches positive and negative infinity. So this will be limit as x approaches negative infinity, negative e to the 2x over negative e to the x plus e to the 2x. That will give us a value of 0. Limit as x approaches positive infinity, negative e to 2x, negative e to the x, plus e to the 2x. This would give us a value of negative 1. Therefore, we can conclude that the horizontal asymptotes would exist at y equals 0 and at y equals negative 1. And for the vertical asymptotes, they would exist at x equals 0. Moving on to part B, the question asks us to find the intervals of increase and decrease. This involves finding the derivative of f at x. So f prime at x would equal 2 e to the x followed by 1 minus e to the x minus, I'm using the quotient rule in this case, negative e to the x followed by e to the x over one minus e to the x squared. I'm going to simplify that. Get e to the x minus e to the 2x, I'm expanding in this case, plus e to the 2x over 1 minus e to the x squared. Simplify that even further, you get e to the x over 1 minus e to the x squared. Let f prime at x equal to 0. 0 equals to e to the x over 1 minus e to the x squared. 0 equals e to the x. E to the x can never equal to 0, so therefore there is no value of x that would equate to 0 in this case. Therefore x does not exist. Now what we have to do, we have to find where the derivative does not exist. So let's take the denominator, 1 minus e to the x squared. Let's equate that to 0. 1 minus e to the x equals 0. E to the x equals 1. And x equals to 0. X equals 0 is not in the domain of the function. Therefore, there are no critical values. What we can conclude from that is that therefore f at x is always increasing. Part C is asking us to find the local maximum and minimum values, but because f at x is always increasing, there are no maximum or minimum values that exist. Part D is asking us to find the intervals of concavity and the inflection points. This requires us to find the second derivative. So we have 1 minus e to the x squared times e to the x minus e to the x negative 2e to the x 1 minus e to the x all over 1 minus e to the x to the 4. I'm using the quotient rule in this case. E to the x 1 minus e to the x squared plus 2e to the x 1 minus e to the x all over 1 minus e to the x to the 4. Let's continue. 1 minus e to the x, e to the x, 1 plus e to the x over 1 minus e to the x. To simplify this, we will get e to the x 1 plus e to the x 1 minus e to the x cubed. We will let f double prime at x equal to 0. When we do that, we get this e to the x 1 plus e to the x. In both cases, x does not exist. Therefore, it does not exist. But where does f double prime at x not exist? Let's find out. 1 minus e to the x cubed equals 0. 1 minus e to the x equals 0, taking the cube root of both sides. E to the x equals 1, and x equals 0. Therefore, we can conclude that there is, in fact, an inflection point at x equals 0. Something to note, When the first derivative at -1 is greater than 0 and the interval is negative and infinity and 0, the graph is concave up. When the second derivative at 1 is less than 0 and the interval is between 0 and infinity, the graph is concave down. So for part E, we are asked to sketch the function based on the information that we've come up with from parts A to D. Just to reiterate, we have a horizontal asymptote at y equals 0, another horizontal asymptote at y equals -1, a vertical asymptote at x equals 0. The function is always increasing, which means there are no maximum or minimum values. Something to note, f at x on the interval -infinity to 0 will always be positive, which means it will never touch this horizontal asymptote at y equals -1. It is concave up from the interval -infinity to 0, which looks something like this. And concave down, that's roughly the shape, from the interval 0 to infinity.